We're going to start off the morning with a multiple choice practice question. You're going to do it yourselves. I'm going to give you 2.5 minutes to do it, and then when you're finished it, we'll take a look at it as a group here. All right, everyone. This one says two conducting spheres have identical surface areas. What are they really telling us there? Something that they probably don't need to tell us, probably wouldn't change the way we do the question, but they're just giving us detail in case you're one of those people that are thinking of all the different remote possibilities here. Okay, when they tell us that they have identical surface areas, they're telling us when these two things touch each other, they're going to balance out, right? They're identical objects, they're going to balance out. Remember we said if you get different sizes, different shapes, different surface areas, and so on, charges might not quite balance out. They try to balance out, but they might not quite do that. Okay, they're telling us here that, look, they're close enough to being identical objects that the charges are going to balance out here. So they have identical surface areas. Sphere A has a charge of 4.50 microcoulombs. B has a charge of -2 microcoulombs, and it's a negative as well. A and B are brought into momentary contact, and then they're separated by a distance of 2.5 centimeters. We've seen this information before, right? We just haven't seen this question before. We want to know in this question what the magnitude of the force is exerted by A on B. What's the big thing with this question that we have to recognize so that we don't make the common mistake that lots of people will make? Yep. Yeah, they touch each other. So when they touch each other, they got to balance out. Let's say 4.50 microcoulombs plus -2.40 microcoulombs divided by 2, that gives me, I think it was 1.05, wasn't it? 1.05 microcoulombs. Now that's both of them, 1.05 microcoulombs. So now that we want to find the force, hey, by the way, before we find that force, what kind of charging is that? It's charging by induction or charging by conduction? Yep, that's conduction. How do you know it's charging by conduction? There's two ways that we know. One is they touch each other. What's the other way? There's a transfer of charge, right? When they touch each other, it's got to be conduction. When they transfer charge from one to another, it's got to be conduction as well. All right, so K is 8.99 times 10 to the 9 times 1.05 times 10 to the minus 6. You can check that on your data sheet to see what the microcoulombs is, right? 10 to the minus 6. And we divide that by the distance squared. We're going to make it 0.025 squared, or we could say 2.5 times 10 to the minus 2 squared. And I got a feeling it's 15.9? Yes? 15.9 newtons. Okay. Anybody forget to touch those charges together? Everybody remember to do that? Good. Good. Excellent. All right. We had a little bit of homework last night. On page 533. Let's take a look at that homework now, keeping in mind that as we're doing that with these problems, and these are pretty common problems to see on exams and tests, with these problems, usually you get 3 objects, and usually in a row. And when you have 3 objects in a row, you've got to draw a free body diagram for the one that you're trying to find the force for. So, for instance, Bailey, if you're trying to find the force for the middle one, and it's a positive, then we're going to draw a free body diagram for the middle one. It's going to experience a force to the right caused by the first one. We'll call that F12, and it's also going to experience a force to the right caused by the third one. We'll call that F32. It's pushed away from number 1. It's pulled towards number 3. We go through that process for every question we do. We calculate each of those forces, and then when we calculate each of those forces, we add them up. We say F net is equal to the sum of the forces F12 plus F32. In this case, F12 and F32 would both be positive numbers, but there are situations in which one or both of them might be negative. Maybe this is a positive charge over here, not a negative charge. That would cause the force of 3 on 2 to be to the left, because this would be pushed away from number 3. And if that was the case, they would make F32 a negative value. Okay, that's it. That's it. It's really just free body diagram stuff that you did in Physics 20, along with force calculations that we've done over the last few days in Physics 30. 2 questions last night for homework, 1 and 2. Any issues with either of those? Number 2? Oh yeah, that's it. That's a tough one, isn't it? Anybody get number 2, by the way? Good for you. Good for you. That's a tough question. Yeah, we can. 1 is certainly a more straightforward question, one that you're more likely to see on a test or an exam. But number 2 is a good thinking question as well. Number 1. So we got a charge here that's to the left of a second metal sphere. We'll make this at negative 2.5 times 10 to the minus 9 coulombs. Charge 2 is over here. Distance is 1.50 centimeters. And then we've got charge 3 over here, which is 2 centimeters to the right of that one. Charge 2 is positive 1.50 times 10 to the negative 9 coulombs. And charge 3 is negative 1.00 times 10 to the minus 9 coulombs. And we're trying to find the force on the second sphere. So as we do that, let's pretend object 3 isn't even there. Okay, let's just look at object 1 and object 2. They attract each other, right, because they're opposite charges. If they attract each other, number 2 is going to be pulled to the left. It's pulled to the left as a result of being attracted to number 1. Now, number 1 moves to the right, but we're not looking for the force on number 1, so we're not going to pay attention to that. 3 and 2, that's an attractive force. Which way is 2 pushed or pulled as a result of charge 3? Guys? If 2 is attracted to number 3, which way does it go? To the right. Good. So we're going to say F12 is an attractive force towards number 1, and F32 is an attractive force towards number 3. Let's get both of those forces now. We divide that by the distance. Make sure you convert that to meters, right? 0.015 meters. And don't forget to square that. Does anybody have a value for that? You have a value? No? 1.49 times 10 to the negative 4. Okay, and we're going to find F32. It's going to be that constant times 1 times 10 to the minus 9. Notice I'm dropping the signs of the charges when I'm putting them in, right? Okay, it's especially important in these questions that I drop the signs of the charges. If I put negatives into these equations, then I'm going to end up with a negative force sometime, and I'm going to think that that means it's to the left, but it's not, right? Just because we have a negative charge and it would provide us with a negative force doesn't mean it's a force to the left. That's why we drop the signs of the charges. 1.5 times 10 to the minus 9 is the other charge. And the distance this time is 0.02 meters. What do we get for that one? Jack, do you have that one? .37 times 10 to the negative 5 newtons. Now, we're going to add those up, but when we do that, F32 is going to be a positive value, and F12 is going to be a negative value. When we do that, we should end up getting 1.16 times 10 to the minus 4. Does that make sense? Good. You want to volunteer where your mistake was? Okay, well, let's go through that process of adding it just to make sure here. The net force is equal to, we're going to say the first one is negative 1.498 times 10 to the minus 4 plus positive 3.37 times 10 to the negative 5 newtons. And we'll pull a calculator out to do this. We get negative 1.498 plus 3.37. And we get negative 1.16 times 10 to the minus 4, which is what we have for answer. Okay. All right. 2's the tough one. 2's the tougher one. Okay, we got 1 or 2 people getting number 2. That's good, actually, for a question that's that challenging. Honestly, though, the challenge from this comes more from the math than it comes from anything else. This one says, in the situation described above, the first and third charges are in the original positions. So let's go here. First and third original positions. They're going to be 3.50 centimeters apart from each other, because that's what they were in the first question, and they're in their original positions. That's how far they're apart from each other. Now, charge 1 still has a charge of negative 2.5 times 10 to the minus 9. And charge 3 still has a charge of negative 1.0 times 10 to the minus 9 coulombs. Charge 2 is somewhere in the middle, although not necessarily exactly in the middle. We want to know where charge 2 has to be in order to experience a net force of 0. In other words, in order for the force of 1 on 2 to balance the force of 3 on 2. Anybody want to take a stab roughly where it's going to go? In the middle, closer to the left, closer to the right? Why do you say closer to the right? Good. Good. If you want the force of 1 on 2 and the force of 3 on 2 to balance, because charge 1 is a bigger value, okay, it's going to have to be a bigger distance as well to balance the other force, right? You get a bigger charge, it's going to give you a bigger force. Well, unless you increase the distance, which is going to give you a smaller force to kind of balance it out that way. So charge 2 has the same value as it had before, plus 1.5 times 10 to the minus 9 coulombs, but we don't know exactly where it's going to go. Here's what I want to do. I want to label this distance between 1 and 2 as r. I don't know what the value of r is. That's what I want to find, right? Where is it? If that's r, then what would this be? Distance between 2 and 3. It's going to be 3.5 minus r. If you don't believe Jack on that one, then add these up. R plus 3.5 minus r gives me 3.5. So we want to find the value of r. We want to find out how far to the right of charge 1 charge 2 is. Now, the other thing we know is that these two forces, at least the magnitudes of these two forces, have to be equal to each other. So we're going to say the force of 1 on 2 magnitude equals the magnitude of the force of 3 on 2. That means that k q1 q2 over r squared is equal to k q3 q2 over what? 3.5 minus r, although we're going to make it 0.035, right, because we want to be in meters now that we're putting it into an equation. And then, of course, we got to square that. Now, got some good news here. The good news is that k appears in both, so we can cross that off, cancel. q2 appears in both, actually, so we can cancel that. Mathematically, that makes life a little bit easier. We've got q1 over r squared equals q3 over 0.035 minus r squared. Okay, now we know the value of q1 and q3, so there's only really one unknown here. q1 is 2.5. Again, we're dropping the sign of the charge, times 10 to the minus 9. Q3 is 1.0 times 10 to the minus 9. More good news. We can actually cancel out the 10 to the minus 9. Cancel out the exponent. We don't have to do that, but it's a little bit easier plugging it into our calculator if we don't have these exponents. So now it's actually looking not so bad. We got 2.5 over r squared equals 1.0 over 0.035 minus r squared. Now, I don't know about you, but the first time that I looked at this question, and that was a while ago, but the first time that I saw this question, the thought that came to my mind at this point when I saw this, thought I got to solve for r somehow, didn't like the word that came to my mind. It's a bad F word. FOIL. Anybody think that too? Anybody see that and think, oh no, I'm going to have to FOIL this? No? No? Good. Good, because you don't have to. I hate foiling things. I hate it. I don't know why, but I don't like it. But the good news is we don't have to do that here. What's the easiest way to simplify this? Not FOIL it. The easiest way to simplify it is to square root it. We can do whatever we want to it as long as we do it to both sides. So let's square root both sides. What's the square root of 2.5? 1.58 over r, because the square root of r squared is r. Square root of 1 is 1. Square root of 0.035 minus r squared is 0.035 minus r. All right, now it's looking better. Still a little tricky here, but looking better. Let's cross multiply. So let's take the r up, and let's take this up as well. So it becomes 1.58 times 0.035 minus r equals r. Now let's distribute the 1.58. Let's multiply it by every term inside the brackets. What's 1.58 times 0.035? (0.05534) minus 1.58 r, right? Because 1.58 times r is 1.58 r. Let's take this to the other side by adding. Becomes 2.58r, because 1r plus 1.58r is 2.58r. And now, if I take the 2.58 over by dividing, I'm pretty sure the value for r that I'm going to get is going to be 0.214, or 0.0214 meters. So the distance of the second sphere from the first sphere is 2.14 centimeters, which we predicted, right? We predicted at least that ballpark. We got a total distance of 3.5 centimeters. We predicted it was going to be closer to charge 3 than it was charge 1, and sure enough, worked out to be. One more example today, and then we're done for the week. 10.5, page 534. Small metal sphere with a negative charge. So to the left of another one. Okay, that's A, B. This one's negative 2.1 times 10 to the minus 6. This one is positive. No, I got positive 1.5 times 10 to the minus 6 coulombs, and the distance between them is 0.0200 meters. All right, then it says a third sphere is, a third sphere is below the second sphere, directly below. What is it? Positive 1.8 times 10 to the minus 6 coulombs, and the distance is 0.0300 meters. We want to find the net force on B. I'll tell you what. I think you guys could do this question right now by yourselves. I don't think you need my help with this. We haven't done one like this. But where have you done, besides what we've done over the last couple of days with Coulomb's law, I mean, clearly that's important to this question, where have you done something that would help you with this? The last unit, sure. Okay, momentum, two-dimensional questions in physics 20, sure. So two-dimensional momentum questions, two-dimensional displacement questions, two-dimensional force questions, back in physics 20, right? They're all the same. Draw your free body diagram. Okay, the force of A acting on B is to the left. That's my fab force again, because B is pulled towards A. Now, C is positive, B is positive. C is going to push B upwards. So the force of C on B is upwards. What are you going to do with this? Get the values. Get the values of FAB. Okay, and that's pretty straightforward, right? KQA, QB over R squared. Get that value. Get the value of FCB. And again, that's pretty straightforward. You got all the numbers there. And then what are you going to do? FAB plus FCB, going to add up the forces? Well, we are going to add up the forces, but we're not going to add up the forces like this, because this is a one-dimensional thing, right? We're going to add up the forces like this. Here's FAB, whatever its value is. Here's FCB, whatever its value is. And we're going to find the value of the net force acting on charge B right there. We can find that by the Pythagorean theorem, and then we can find the angle by the inverse tan function. This is just physics 20, right? Boy, it's funny. We go through these questions, and this has happened a few times now. We go through these questions for a few days in physics 30, and then we make it harder. But by making it harder, we're actually adding physics 20 to it. So I don't know if it's any harder. It just is a little bit more. That's all. Right? A little bit more work. That's all. All right. You guys okay with that, or should I go through the numbers there? Comfortable? Confident? Okay. And I think you can handle these two questions on page 534.